The final new technique that we're going to talk about on our techniques of integration is we're going to take another look at integrating rational functions. Now, I want to go back to the very beginning, pre-calculus wise, and remind you some things about rational functions and how we can deal with them using algebra. But sometimes algebra is not enough to manipulate the integrand. Sometimes we've got to use this technique that we're going to talk about. So a rational function, remember, by definition, is the quotient of two polynomial functions. So it has a polynomial in the numerator and a polynomial in the denominator. Nothing but power terms in the numerator and the denominator. Remember, it's important for us to determine whether our rational functions are proper. And a proper rational function is one where the degree of the numerator is less than the degree of the denominator, the highest degree term. Here, the power term in the numerator has an exponent, and the highest degree term in the denominator is 3. So this is a proper rational function. Here, the highest degree is 1 in the numerator, and the highest degree is 2 in the denominator. So again, it's proper. But look over here at this one. This is why we say this one is improper. The highest degree term in the numerator is 5, and the highest degree term in the denominator is x cubed. So this is improper, and we can't do calculus. We cannot evaluate an integral on an improper rational function. So we have to do an algebra technique to turn it into a proper rational function. And what we're going to get is we'll get a polynomial function and a proper rational function, and we use polynomial long division. So let's do an example. This is the rational function that we had on the other slide, and the numerator is under the division symbol and the denominator is out front because we're taking the numerator and dividing it by the denominator. And we had a definite process to do this. So let me remind you of the process. We take the lead terms inside and outside, and we ask ourselves, what do I multiply this by to get it to equal that? And that's what we're going to put right up here. So if I multiply x cubed by x squared, the result of that is x to the 5th. I'm going to get rid of that, clean it up a little bit. So there's x squared. This gives me x to the 5th. Now the next step in the process is to take what I put up here and multiply it by every term out there. So not only am I going to multiply x squared by x cubed, but I'm going to copy down the plus sign and I'm going to multiply 5x by x squared. So that gives me a 5x cubed. Now we're going to subtract that from our polynomial that was in our numerator. And remember, it's important to put the parentheses around there because when you're subtracting, you want to make sure that you distribute that negative all the way through. So I have x to the 5th minus x to the 5th. That goes to 0. Now I have 2x cubed minus 5x cubed. That gives me a negative 3x cubed. And now I'm going to copy down what's left up there. And now I just repeat the process that I did. What do I need to multiply x cubed by to have it look like negative 3x cubed? Well, that's a negative 3. So I multiply it by negative 3. That gives me a negative 3x cubed. I multiply 5x by negative 3. That's minus 15x. Put parentheses around it and a minus out front. So 3x cubed minus a minus, or plus 3x cubed, gives me 0. Negative x plus 15x gives me 14x. And then I just need to remember to bring down my plus 1. Now, the minute that the degree here is smaller than the degree there means we're done. This now becomes our remainder. And just like we learned when we were doing numbers before variables showed up in our work, we take what we found as our answer, and then we add to that by putting the remainder over our original denominator, what was called the divisor. So now, just as we said a while ago, we can turn an improper rational into a polynomial plus a proper rational expression. And this one is proper. The numerator has a degree of 1. The denominator has the highest degree of 3. So now that is a proper rational expression. So remember that sometimes we can evaluate our integrals on our rational expressions just by doing polynomial long division. But in the case where we can't, in the case where that doesn't work for us, sometimes we may need to take our proper rational function and try to decompose it, try to come up with the two fractions that were added together originally that gave us this resultant polynomial function. And so this technique is called partial fraction decomposition. So we've been adding fractions since grade school. Let's talk about just simple adding of fractions. 1/3 plus 1/4. Let's talk about what that process looked like. Well, the first thing that we did is we found a common denominator. And usually that common denominator was just the product of the two separate denominators of our fraction. Then what we did is we had to multiply each one of those fractions by what was called, it's called many things. A well-chosen one is what I've heard it called most often. A well-chosen one. We're looking for something with the value of 1 that's going to manipulate our original fractions the way we want them to. So we want the result of this product to have a denominator of 12. So what can I multiply 3 by to give me a denominator of 12? Well, that's 4. But I don't want to change the value of my original fraction. I just want to change the way it looks. So I'm multiplying the numerator on this fraction. I'm multiplying 4 times 1. Now I'm going to do the same thing over here. The result here of this product, I need the denominator to be 12. That means I have to multiply 4 by 3. I don't want to change the value of 1/4. I want the result to still have a value of 1/4. So that means I'm multiplying this numerator by 3. So the result of adding those two fractions is 7/12. And that's the process that we go through to do that. Well, let's say we reversed that. Let's say we had two fractions. We knew one of them had a denominator of 3 and the other one had a denominator of 4. How would we go about finding what their original numerators were? We don't know that they're 1. We do now because we just did it in the other direction, but let's say we didn't know. Well, let's say this was A and this was B. And so we could decompose these two fractions and we could find the value for A and we could find the value for B, and then we would have something that was equivalent to that rational expression. So let's go about doing that with variables involved. So here we have a proper rational expression. We know enough algebra to be able to factor the denominator. The beauty part is when variables show up, we don't really have to worry about how to factor it. It'll pretty much only factor one way. Where if our denominator was 12, well, that's 1 times 12, or 3 times 4, 2 times 6. When variables show up, there's really only one way to factor it. So we would factor the denominator, and we would realize that it was the sum of two separate fractions. And so we would write those two separate fractions with A over one denominator and B over the other denominator. And then we would use this information to actually find the value of A and B. So we're going to do partial fraction decomposition. Let's say you were given this integral, 3x minus 1 over x squared minus x minus 6. The first thing we want to look at is Is it proper? Yes, it's proper. The next thing we want to look at is it u substitution? So we would take what's on the denominator, call it u, we would find du, and we would really try to rewrite that in terms of u and du. Here's the only problem. We're off by more than just a constant value. There's nothing I can do to 2x minus 1, nothing I can multiply it by, nothing I can do to make it equal to 3x minus 1 or to some constant multiple of that. So this is not a u substitution problem. So now we would just have to drop back and say, well, there's absolutely no way we can evaluate this integral. But that's not true if we realize that maybe we can decompose and come up with two fractions, and maybe we can integrate those separate fractions, because integrals do break up over addition. So let's factor the denominator. It appears to me that the denominator is x minus 3, x plus 2. So one of our fractions has a denominator of x minus 3. The other has a denominator of x plus 2. Well, what were their original numerators? How do we find a and b? Well, here's how we're going to find a and b. We have a over x minus 3 plus b over x plus 2, and that has to equal 3x minus 1 over the product of those two linear factors. So how did we get there? Well, let's go back to what we originally did. What we originally did is we took this fraction, copying what we just did a while ago with 1/3 and 1/4, and we multiplied it by a well-chosen 1 that would make the result have the common denominator that we were after. And we only wanted to multiply it by something that had a value of 1. We couldn't change the value of our original fraction. We only wanted to change the way it looked. So this looks like a times x plus 2. And let me clean that up a little bit. So what we're doing is we're multiplying a times x plus 2. We're going to multiply b times the factor that is not in its denominator. So b gets multiplied by x minus 3. But we're actually doing, even though we're not showing the work, we're doing the well-chosen 1 multiplication. And that has to result in the numerator. The numerator has to come from those well-chosen 1 multiplications. So we have ax plus 2a plus bx minus 3b, and all of that has to equal 3x minus 1. So let me ask you, what determines the coefficient to x? How did this 3x happen on the right-hand side? Well, the only two players over here, the only two terms over here that have anything to do with x are those two terms. So it has to be true that ax plus bx equals 3. Or what we'd say, if we were really comfortable, is a plus b equals 3. Well, that's cool, but I still don't know what a is, don't know what b is. I just know their sum is 3. So let's look at the other terms. These terms are what determine our constant value, -1. So it has to be true 2a minus 3b equals -1. Now I have a system of two equations. And I can use algebra to solve that system of equations. I'll pick up here in the next video.